Dr. Nina Welti, who is based at the CSIRO Agriculture and Food Labs on the Waite campus, describes herself as an isotope biogeochemist. Nina is going to tell us all about important and exciting research conducted here on the Waite campus that is enabling us to trace the origins of our food and drink. Nina, thank you.
Do you wonder where your food comes from? We often closely read the labels to check to see we've bought products when we know their origin. It's because we value these products from where they come from. But how sure are you that you know what you've gotten? We trust these products because how could smiling cows be dishonest? With the globalization of agricultural markets and the convenient transportation of food across countries and continents, the potential for mislabeled products increases, highlighting the need to be able to determine the country of origin. When we buy Australian barramundi fillets, we expect that only Australian barramundi is in the product. But what if it was Asian sea bass instead? When we buy Swiss cheese, we expect that those cows were living high in the Alps, not in the flats of Texas. How sure are you that you know where your frozen berries have come from? Producers and consumers use geographic origin, or provenance, as a way to identify products they trust and value. We, as the public, participate in this trust agreement, but we at CSIRO would like to rely on facts, not our emotional trust. So identifying the provenance of high-value foods like nuts, fruits, wine, and beef is a goal for us at CSIRO, in collaboration with farmers, retailers, administrative authorities. We believe that where our food comes from matters. After all, we know that South Australian wines taste way better than the snooty French ones. The site, such as the paddock or the field, is believed to leave an influence on the food itself. This is the idea of terroir. Terroir is the microclimate. It's the temperature, the humidity, access to rainfall, amount of sunlight. Any slight modifications to any of these may eventually change the taste of food. That's why, even when foods of the same kind are grown in different places, they may have a different taste. We value terroir. There's a reason why champagne can only come from Champagne, France, and not just any old random clean skin from Dan Murphy's. We trust those grapes and those producers to make a quality wine that we all know and value. If only the location where a food was grown left a mark. Luckily, it does, and we can follow that and trace these foods as they move around the globe. So if you remember your high school chemistry class, way back when, there was probably a periodic table of elements hanging on the wall somewhere. We learned that elements of nature like carbon, nitrogen, oxygen are arranged on the table based on how much they weigh. An element's weight is determined by the number of protons and neutrons it has. Oxygen is number 16 on the table, meaning it has 8 protons and 8 neutrons, almost all of the time. But 0.2% of the time, which is the same chance you and I have of being hired at Google or Port winning any kind of grand final, oxygen has 8 protons and 10 neutrons, making it slightly heavier and weighing 18. We call these different forms isotopes. The slight difference in weights means that the heavier oxygen reacts slower, just like I'm much slower after eating a heavier meal. So how does this work with our food? We can imagine that this pink ball is our common oxygen, R16, and this black one is our heavy O18. So if we have 1,000 oxygen atoms, 998 of them will be pink and 2 will be black. So the molecule O2 is made up of 2 oxygen atoms. Generally, we'd have 2 pink isotopes, 2 common isotopes. Sometimes, but very rarely, we'd have 1 light and 1 heavy oxygen. And very, very rarely, we'd have 2 heavy oxygens. So let's look at how this works in practice. So imagine that I'm standing in the middle of the ocean, and you, the audience, are the plants growing on the continent of Australia. Up front, we've got the coast, and further back, we go inland. So, as water is in the ocean, it's considered to be at isotopic equilibrium. just like this bin of pink and black balls. They're not changing anymore. But as clouds begin to form, the light isotopes will evaporate first, creating clouds which are slightly lighter than the ocean behind them. As these clouds move to the continent and turn to rain, the heavy isotopes are going to fall out first, so that the rain is slightly heavier on the coast than it is inland. As the rain begins to move into the continent, the light isotopes are left. There are fewer heavy isotopes to catch. And over time, we can measure the isotopes of rainwater in different locations and link the average ratio to a location. This happens consistently over time because it's a physical reaction. There's no chemistry involved in this. So this pattern will be persistent. You, as the plants of Australia, have taken this water to grow. Now, and just as we can look at the color of glitter left on your hand to guess where you were sitting, so too will the plants have taken up that rainwater and that oxygen isotope. Now, plants don't stay in one spot after harvest. And just like you'll get up to leave after this talk, to get the next talks, the glitter is gonna follow you around. No matter what you do, you can't get rid of it. Trust me, everything I own is covered in glitter now. The same happens with our plants and our food products. The intrinsic oxygen isotope ratio remains the same no matter where the plants and products move around the globe. So we can measure the isotopes of a product, wherever it may be, and determine where it's come from. We can then tell the difference between sugarcane grown in Queensland and sugarcane grown in Mexico. The water used to brew an Irish whiskey is going to be much different than a Kentucky bourbon. Wines that are labeled for Australian export markets can't be mixed in another country with water to increase their volume. We'd be able to tell the difference in isotope ratios. The impact of this isn't limited to where your food has come from. We can also measure what's eaten your food. So we know that vegetarians are slightly different than carnivorous friends. We can follow rupu around the country and look at the change of kangaroo diets in relation to water stress and migration patterns. We can also use this to unravel complex food webs like those in the Murray-Darling floodplains to look at the impact that water management decisions have on indicator species like the Murray cod. This can have long-reaching effects as it can be used to weigh the benefits for society against the needs of the environment. So using the science of tracing isotopes around the country, along with innovative mapping, we at CSIRO are giving producers an opportunity to invest and promote the unique character of their local products, a brand for their own location. And this brand can be champagne, it can be Vidalia onions, Bruny Island cheese, so that you know whenever you buy that product, you can be assured that it's come from where it has said. So we have taken a global view of how food is produced, sold, processed, and certified in order to understand the value chain and provide an opportunity for producers along that chain to trust their labels. This requires a collaboration between farmers, retailers, CSIRO scientists, data managers, and administrative authorities. After all, we all want to know where our food comes from so that we can be assured that a barramundi isn't a cow from Texas. Thank you.